Welcome to the NASA High Power Rocketry video series. In this video, we will be discussing payloads and avionics. One of the most exciting parts of high power rocketry is that high power rockets can fly systems that perform certain tasks. We call these payloads. The payloads can be used for a recovery system, an engineering package, a tracking system to locate the rocket, and/or a scientific experiment. One of the most basic payloads is an altimeter to record the altitude of the rocket in flight. The altimeter needs a power supply and a switch in order to be turned on. Since most altimeters sense barometric pressure, they use a pressure transducer to determine the altitude based on the change in pressure since the rocket left the ground. For this reason, it is important to have a small hole in the airframe so that the altimeter will be able to sense the ambient pressure outside of the rocket. A few altimeters used in high-power rocketry are accelerometer-based and use the acceleration data to determine the altitude. Since these altimeters do not measure the air pressure, it is not necessary to have a hole in the airframe. Hobby rocketry altimeters are very small and can fit in spaces as small as 1 by 3 inches. For this reason, small altimeters are commonly flown as payloads to measure rocket height even if the altimeters are not used to control recovery system events. Another example of a payload is a set of trackers to locate the rocket during its flight. The units transmit a radio frequency to a receiver on the ground. Trackers can operate in a few different ways, and we will discuss the two most common. The first is simple radio frequency transmission. With radio frequency transmission, a unit on the rocket transmits a radio wave at a certain frequency, and a handheld receiver on the ground detects the transmission. The ground unit emits an audible signal that is loudest when pointing toward the rocket. By walking in the direction that gives the loudest tones, the user can find the rocket. The other type of tracker commonly used is a global positioning system-based unit. These units are often referred to simply as GPS. There are a few common methods in which GPS systems work. In one method, a transmitting unit on the rocket sends and receives signals to GPS satellites orbiting the Earth. These satellites transmit a signal that gives time and satellite position data to a ground-based unit. The ground-based unit then performs a series of mathematical algorithms to calculate the position of the transmitter on the rocket. The position of the rocket is displayed on a hand unit, so the user can see where the rocket has landed. With the other method, the unit on the rocket acts as both a receiver and a transmitter. The unit on the rocket receives the position data from the satellites, does the calculations, and then transmits the position data to a ground-based receiver. Although units that transmit a signal via a simple radio frequency transmission or GPS transmission are useful in locating the rocket after a flight, there are a few things to keep in mind to ensure the safety of the rocket, surrounding property, and most importantly, yourself and others. The trackers transmit energy in the form of radio waves. There are other parts of your rocket that are affected by this energy, and steps need to be taken to ensure that no accidents happen. Your recovery system components can be greatly affected by the radio frequency from the transmitters. The electromagnetic interference from radio waves can adversely affect the sensor data on the altimeter, and the altimeter may incorrectly read altitude data. This becomes problematic when the interference is bad enough that the altimeter incorrectly senses the rocket is at the altitude for parachute deployment. When this happens, the altimeter sends the signal to ignite the electric match, which ignites the black powder ejection charge and deploys the parachute. If this happens on the ground, the ejection charge gases and moving airframe components can cause property damage and serious personal injury. Also, if the electromagnetic interference is strong enough, the resulting energy can actually ignite the electric matches without a signal from the altimeters, thus deploying the parachutes. Another, less hazardous effect is that the electromagnetic interference of one tracking device could interfere with the output of another transmitting device. There are ways to mitigate the effects of the interference on other parts of the rocket. First, the power output of any transmitter should be only high enough for the unit to work effectively. If a GPS transmitter can operate with a power output of 100 milliwatts, then don't use a higher output. The higher the power output, the higher the likelihood of radio frequency interference. Second, create physical distance between transmitting devices and components that are sensitive to radio frequency energy. If the recovery system circuitry is in the middle of the rocket, it is a good idea to put a transmitting device in a separate and isolated part of the rocket. The nose cone is a popular place for rocketeers to put tracking system transmitters. This creates enough physical distance between the transmitters and the recovery system circuitry that, assuming proper transmitter power output, there should be no interference between the components. A third way to prevent inadvertent radio frequency interference is to actively shield the components. A popular and inexpensive way to shield the components is to line the inside of the altimeter bay with a metallic material such as aluminum foil. In addition to payload packages that are used for altitude recording and tracking, there are a multitude of possible payload options used for scientific or engineering purposes. These can include atmospheric science, biology, anatomy and human factors, microgravity, aerodynamics, control systems, and many other options. Some of the most popular rocket payloads are for atmospheric measurement. These payloads may measure temperature, pressure, humidity, solar irradiance, or radiation. Sensors for these measurements are readily available, easy to use, and easy to integrate into the rocket. Many student rocket teams fly biology experiments. Plants and invertebrates can be flown to test the effects of the launch forces on the long-term growth and genetic characteristics of the test subjects. Anatomy experiments have included testing the capillary action of blood during the acceleration and microgravity portion of the flight. These payloads support the research of long-term human spaceflight. Some of the more challenging payloads are microgravity payloads. During the brief period of microgravity seen at apogee during the first few seconds of freefall, teams may fly fluid dynamic experiments, control system experiments, gas dynamic experiments, and other microgravity experiments. Some complicated payloads actually deploy away from the rocket at some point during the flight. These payloads can be scientific in nature, but often are engineering-based. One example is a package that is instrumented to sense atmospheric properties. Another example is a deployable unmanned aerial vehicle. These can include gliders, helicopters, or airplanes that can each have its own payload package. While deployable payloads are exciting, they complicate the recovery process. One must ensure the deployable payloads have a dedicated and reliable recovery mechanism that is flight-worthy. When choosing a payload, it is important to keep in mind that the range safety officer has the authority to make the final decision on whether or not a project flies. As such, it is important to communicate clearly and thoroughly about your intentions to fly any payload. If flying the payload creates a flight profile that is outside the realm of normal high-power rocketry flight, it is good practice to contact the local club's prefect and range safety officer well ahead of the day of the flight. Describe the project in mind and answer any questions they may have. Safety is paramount, and any questions about a particular project or an outright refusal to allow a particular project to fly because of elevated risk should be observed. Remember, the range safety officer is the final authority. Thank you for watching this NASA high-power rocketry video series.